Let us now discuss a very important topic, and that is inrush current limiting in rectifier diode capacitor filter circuit. This inrush current limiting is a very serious problem in the rectifier diode capacitor filter circuit. So what it basically does is that in the circuit, as we see here, you have the source connected through a switch and through a diode bridge rectifier like this, and then you have the capacitor here, and this is the V0 across the load, and the load may be resistive or any other power supply itself. Now the problem here is that the source, the current from the source passes through the switch during on condition, which is a very low resistance, passes through the diodes in the forward biased condition, which is again very low forward resistance, then passes through the capacitance and back through this diode and the source. Likewise, in the negative direction also, it takes the alternative path. The problem here is that you have very low negligible impedance in the path, the current flow path for the current to flow from the source to the capacitor to charge it up. So at the time of startup, when you are switching on the switch, you can expect a very large inrush current to be drawn from the source, and this large inrush current can blow up these diodes or even the capacitor. And we have designed all these diodes and capacitor to operate only in the steady state condition. So this implies that even though the diodes and the capacitors have been designed for steady state operation, the moment you switch on the circuit, by switching on the switch, the components will blow and the circuit will not operate. So every time you switch on the circuit, there will be components blowing. So how do we overcome this problem of inrush current limiting? Now that is the discussion now that we will see. You can now consider the source Vi connected through the switch, flowing through the capacitance and connected in this fashion. So the source Vi having a voltage Vi, and if you switch on the switch, close the switch, you will expect a current to flow through this path, and this at the time of startup is called the inrush current, and this can be very, very high. Why will it be very, very high? Now let us say that you have Vc as the variable indicating the voltage across the capacitance here. So the inrush current is difference in this potential, so that is Vi minus Vc, divided by whatever is the path impedance. Now the path impedance is comprised of the impedance of the source, which will be very low, the impedance of this closed switch, which again will be very, very low, and ESR the capacitance again low, and track impedance, wire impedance, and so on. So therefore the impedance in this path is very, very low, and that Z is tending to 0. So let us imagine a situation where when you are starting, so at the time of starting, Vc is 0, so this is 0, and the inrush current is given by Vi by Z, and Z is very, very low. And as chance may have it, at the time of switching this on, Vi, worst case possible, can be Vi peak, the max possible value in the sine wave. So that value divided by Z can be a very, very large value. It can be thousands of amps, and this is thousands of amps these diodes are not designed for, and they will blow up. So every time you switch this on, these diodes will blow up, or the capacitor will blow up, and this circuit will not function at all. We have designed these diodes and capacitor to function in the steady state, but we are not able to take the circuit into the steady state because of this inrush current problem. Why should the circuit operate during the steady state? So at the steady state, the capacitor is fully charged, and this is fully charged, so this is close to Vi peak. So Vi peak minus Vc, which is close to Vi peak, will be a delta V divided by a small divided by the Z, will give you significantly lesser inrush current, and that value is what we have designed these diodes for and the capacitor for, to handle these currents. So in the absence of this charge here, you can expect a very large inrush. And how do we make the transition from the switch on transition dynamics to the steady state dynamics where these components can handle the current? Now that is where we need to put some circuits here which will make the transition, startup transition, and then hand the baton over to the steady state portion, and the steady state portion, the diodes and the capacitors will behave as we have discussed in the last week. So let us now see what circuits we need to interpose here to make the circuit operate even during startup and transit nicely and smoothly into the steady state operating mode. Now let us see what happens to the wave shape when the switch is closed. So let us draw the x and y axis, and let us say that this is the rectified input sine wave. Okay, it has an amplitude of Vm, so it's basically Vm sine omega t, and we are taking a benign case where at the time when the switch is being closed, that is t equal to 0, the input wave is at 0 and it rises in a sine fashion. So you are synchronizing the closing of the switch with 0. Under such conditions, what happens? So this is the t axis, and you will see that there is a large inrush current, and that is corresponding to this I here. I will mark it here. It's a large inrush current here. And what happens to the voltage waveform, output voltage waveform? This voltage waveform will rise here along with Vi up to this point, and then the Vi is falling, the diodes are reverse biased, then this will start going down in this fashion depending upon this load. And then again when Vi crosses and forward biases the diode here, you will see that it charges, the voltage follows the input wave shape, so on this repeats. So here actually you have reached steady state. So here there will be a current flow as we have seen in the previous modules. So this will correspond to the charge state of the capacitance. So you will see that this peak amplitude is correspondingly smaller compared to the starting peak. Okay. Now this is a benign case where the switch turn on is synchronized with the 0 crossing of the input, which will not happen in most cases. It will not happen in a practical situation. When you turn on, it may so happen that the input is at its peak, at the worst case condition. And what happens? Now consider the worst case condition where at the time of switch on of the switch, it so happens that the input voltage is at its peak value. The Vm is at this point, suppose sine wave. So this could happen. This is the worst case condition. If this happens, what will be the peak inrush current? The steady state portion, there is no change. It will be similar to what it was here. During this point, it is Vm, and it is Vm by impedance Z. The Vc is 0, that is a charge on the capacitor is 0, therefore no voltage. So you will have a very large overshoot. I just want to show the relative magnitude will be something like that. It will be much higher than what would be for a synchronized switching where Vi starts from 0. So this could be a very large value. It could go to thousands of amps. So this is the current here, and the capacitor voltage quickly builds up to this value, and then the diode cuts off, and then the steady state starts. So you see that it is during this time the entire problem occurs, and during this time itself the diodes will blow, and you will not be able to take it to the steady state. You can in fact verify this by simulation. In the previous modules, I have shown you the simulation of rectifier circuit in ngSpice. You could probably get some insight by doing some simulation on that. Probably I will show you a quick example.